One of the most common topics that seems to come up in support is the subject of unbraced lengths in RISA-3D. If I click on a member, go into my Properties menu, and expand the Design Properties, I can specify bracing via several unbraced length options, which can be seen here. These options do not provide physical bracing to the model for analysis, but rather they affect a particular member's capacities calculated for code checks. To expand on this, we have provided a simple model which will demonstrate that a member's capacity for compression, as well as flexure, are dependent on the spacing at which elements provide bracing along the length of a member. Let's start by taking a look at the various unbraced length options for a given member. The LB values, LBYY and LBZZ, represent the distance between points which brace the member against flexural column-type buckling about the member's local Y and Z axes. These values are used to calculate the slenderness ratios for both directions, which are used in the calculation of the member axial compression capacity. Below that, we have the L-comp values, L-comp top and L-comp bottom. These values represent the distance between points which brace the top or bottom flange of the member against lateral torsional beam-type buckling. These L-comp values are used to calculate the member's flexural bending capacity. It is worth noting that for concrete members, these values do not apply, since they are not checked for lateral torsional buckling. Also, I should mention that for wood members, L-comp top will be referred to as LE bend top, and L-comp bottom will be referred to as LE bend bottom, based on the wood code terminology. Finally, we have L torque, which you can see here. L torque represents the distance between points which restrain the member against twisting about its own axis. These values are used to calculate the member's torsional buckling and flexural torsional buckling capacity. These limit states affect the member's axial compression capacity. Let's take a look at a few beams and columns in order to evaluate how unbraced lengths can have an impact on design results. If we take a closer look at the model, we can see that the beams and columns have the same respective lengths, loads applied, boundary conditions, materials, and shapes. Where they differ is in their respective lengths. For beam 1, we have no entries. For beam 2, we have an entry of segment for LBYY and LBYY for L-comp top, meaning that the segment will be applied to both. The segment command means that where there is a node, the member will be braced. Since there are two segments, the member will be braced into two segments. In the third beam, we have an entry of L-comp top equal to 0, meaning that the member is continuously supported along the top. Alternatively, if we had L-comp bottom set equal to 0, the member would be continuously supported along the bottom. Now let's take a look at the columns. Member 36 has no entries for unbraced length. However, member 34 has an entry of segment for both LBYY and LBZZ, meaning that the member is braced into two segments at this node. Additionally, we know that all of the beams have the same length, loads applied, and materials. However, being that they have different unbraced lengths, they will have different code checks. Let's see how this applies. We'll use our select tool. We will filter out our unselected items. And we will open our code checks, and here you can see member 1 has a code check of 3.2. Member 2 has a code check of 1.08. And member 3 has a code check of 0.977. Also, as you can see here, the factored compressive strengths are different for the three members. We get those per AISC Chapter E. Now in the columns, we will also use our line select, and then we will filter out unselected items, go to our code checks, and we should see different code checks per members 34 and 36 respectively. Additionally, we'll see different factored compressive strengths per AISC Chapter E. In order to take a deeper dive into how unbraced lengths affect our code checks, let's open the member detailed reports. If we click on member 1, we can go ahead and put that over here. And on member 2, we can put that over here. We can go to our strong axis flexural analysis, where we will see our unbraced length. Here we have the full 15 feet and the 7.5 feet at the midpoint. This will later come into play for the bending axial interaction check, where we can see that we have different allowable flexural strengths in the strong axis reported. Member 1 with 6.67 kip feet and member 2 with 19.801 kip feet. If we go in for member 3, we'll also see different bending axial interaction check, which actually passes, and you can see that here the allowable flexural strength in the strong axis is 21.87 kip feet. Let's also take a look at these columns. Put member 36 over here, and member 34 over here, where we will see that we have different bending axial interaction checks, as well as different allowable axial compressive strength. Here we have 15.15 kips. Here we have 41.307 kips. As you can see, understanding unbraced lengths and how these lengths impact the capacity of a member is essential to understanding how member code checks are performed. If you have any questions or are looking for a little bit more information, please visit our website, RISA.com, or our online help file at RISA.com/help.